Hey class, Mr. Bean here. This is for AP Physics video 61B torque. Anyways, so before we start, let's try to get a intuitive feel for what torque is. So on this drawing here, we have a wrench that's attached to this bolt here, and we have like position A, and we have like position B, and we have two forces that appear to be the same magnitude. And we want to figure out what is torque. Well, intuitively, if I apply a force here, we feel like that this is going to rotate in this direction, okay? And we're going to call that counterclockwise. Okay, and for purposes of this class, we'll take anything going counterclockwise to be positive. So anything going clockwise this direction here, we'll go ahead. So clockwise rotation, we'll go ahead and call negative. All right, so anyways, so here's the fulcrum. So where is it going to spin at? So this little dot right here is called the fulcrum or the pivot point, okay? Fulcrum. So whenever we do this, we always want to identify where the fulcrum is to help make the problem a little bit easier to deal with. All right, now a couple of things we need to know about this. Okay, we have some forces applied, but there seems to be the forces are applied at some distance away from the fulcrum. So let me go ahead and try to do some different colors here. And let's go ahead and use red. So we have this distance right here, and we'll call that RA. Okay, distance RA right here. Okay, and then we have this distance B here, and we'll use a different color for that. Let's go ahead and use blue. So I'm going to do a dashed line here. And then here we have, we'll call this RB here. Okay. All right. So now also when we notice here, looks like the force is being applied at 90 degrees this is called usually this is called the lever arm. Okay. Sometimes this is called the lever arm. And we'll go ahead and make sure that we get that there. It's called the lever arm. And looks like a force, this is being applied 90 degrees to this and also 90 degrees to here as well. Okay, so let's take a look at this one here. So if I apply a force, it's going to rotate. Okay, and that rotation is called torque. So when a force is applied at some distance from a pivot point, it's going to cause angular acceleration or cause rotational motion. All right. So in this case here, we'll call it torque. Now, there's a symbol called tau, which we'll call torque, and we'll call it torque of A. Okay, so torque of A, how we calculate it is this: there is some distance RA, okay, from the pivot point. We'll call it RA here, and here we'll call this force A. It looks like the two forces are the same. So force A equals force B. So we'll go ahead and call it F here. Okay. So just so we're clear, it appears that force A is going to equal force B. Okay, like so. All right. So we have this here, and also I'm going to go ahead and attach here sine of theta. Okay, sine of theta. All right, so we'll take a look at this here. So let's go ahead and try to simplify this as much as we can. So torque A is going to be whatever RA is, okay, times F, and the sine of 90 degrees is going to be 1. So it's just RF, okay. All right, now over here at B, okay, so torque B, all right, is going to equal whatever RB is, okay, like that here, RB, okay, times F, okay, and is also going to be the sine of 90 degrees. Okay, sine of 90 degrees here. All right, because it's being applied at 90 degrees. So we go torque B here is going to equal whatever RB is, right? RB is here, right? Is RB. And this is going to be the sine of 90, so it's just going to be F. Okay. All right, so looking at this here, what has a greater torque? Okay, so we're applying the same amount of force here, but this will have a greater rotation because the radius is bigger or longer than RA, so this will have a longer torque. Okay, so torque causes rotational motion. All right, now let's take a quick look here and see what we got. So the units of this, of the radius or the distance, is going to be meters, right here, right? And the distance here of force is going to be newtons. Okay, so meters, newtons. Now, however, this is not joule, not joule. Okay, it's not energy, it's torque. So I like to write it. Now, a lot of times people will say Newton meters like this. That's usually how it's written, Newton meters. However, people get confused for this to be energy. So when we're doing torque, I like to do meter newtons, and it's not joules. Same thing over here. This is going to be meter newtons, like so. All right. So torque is what causes something to rotate or have angular acceleration. Just like in Newton's law, when we have F equals ma, it causes an object to accelerate. Well, torque causes an angular acceleration or causes something to rotate. Okay. Now down here we have torque is a measure of the force that can cause an object to rotate about its axis. Okay, and it is a vector quantity. Okay, so it does make a difference. Direction does make a difference. Okay. All right, we'll go ahead and pause here. Then we'll look at some examples. Okay, just to recap here. So torque is analogous to force, okay, where torque here causes rotation, and we have torque is equal to R times F sine of theta, and it's meter Newton, not joules. Okay, and again, force causes acceleration, where this is kilogram meters per second squared, which is newtons. All right, so let's go ahead and just recap that. Okay. All right. Anyways, let's go and take a look at some examples here, and then we'll see. Again, we're looking for some intuitive feel before we start putting some numbers in. All right, look at our first example here. Let's go and use black. Okay, suppose we have we'll call this a massless bar like this here. And let's say it's straight here. And this whole length here, we'll call this length R. So it has some length R here. Okay, and now there's no apparent fulcrum. So what I'd like to do is, if they don't give you a fulcrum, let's go ahead and set the left side here to be the fulcrum. So this here is going to be the pivot point or fulcrum. Okay, again, if they don't tell you where it's at, we'll go ahead and assume it's on the left side. So we'll say fulcrum. Okay, so this is the fulcrum right here. All right, so let's say there's some force being applied right here on the edge. Okay, and we'll call this force F, like so. All right, so if I apply this force F here, and we can ignore friction here, it's going to rotate in this direction here, okay, which is, in this case, clockwise. Okay, so that's going to be in the negative direction. Okay, so we want to know what is the torque here in terms of this relationship right here. So if I do that, we'll go over here and we'll say, well, here's torque. Okay, here's towel. Torque is equal to R, right, times F, and we'll go ahead and say sine of theta. Okay, so we'll see what this means here in a second. So because we can see here that this is going to be 90 degrees, right? So sine of 90. Okay, so we'll make sure we understand that. The sine of 90, and we're in degrees now, right? The sine of 90 degrees is equal to 1. Okay, so this is going to be R times F. Okay, so all right, R times F. Okay, now let's suppose we have the same situation here. Let's drop down here. Okay, here's the fulcrum here. And let me go ahead and kind of draw this out like this. And we'll go the same length. Okay, so again, it's the same length R. Okay, except this time, let's have the force, let's say the force is being applied at some angle right here. Okay, it's the same force, but let's say it's now 30. Let's say this is 30 degrees. So let me go ahead and write 30 in here very carefully. So this is going to be 30 degrees here. Okay, this angle 30. All right, so now let's see what we got going on. Okay, here's the fulcrum again right here. So we're going to say here torque, right? Here's torque is equal to F times the, R times F times the sine of theta. Now I'm going to kind of write it like this now, so it makes it more apparent. Now it's force, but I need the perpendicular component. So what does that mean? Let me go ahead and use red here. So if I go right here, okay, so this is the part I want, this red. That's the perpendicular component of force that's actually causing the rotation. Now remember, it's a vector, so we can actually move it over here, okay? So because this is a vector, I can slide it over here. So this is the component that's actually causing the rotation to occur, right? So if I go over here, We'll go here and write R here. Okay, there's R times, we'll say this is going to be F here. And it's going to be F, it's going to be sine of 30 degrees. Okay, so we want the sine of 30, want the force, the sine of 30 degrees that's actually causing the rotation. That component of the force, the red here, is causing the rotation. So when I do this here, this now becomes 1/2, right, R times F. Okay, so if I compare this to up here, so up here it was 90 degrees, here is 30 degrees. So just by changing the angle at which it is applied causes the force to be reduced by half. Okay, kind of help you out. So kind of think about that. Okay, all right. And also too, it's going to rotate, what we say here, is still going to rotate in the counterclockwise rotation. So counterclockwise rotation, which is negative. All right. All right. So another example here. Let's go ahead and here's our pivot point here again. Okay. And we want the same distance R right here. Okay, so here's this here, and let me go ahead and let's get an eraser real quick here. Let's get this, erase this top part here. Oh, well, yikes. All right, so let's go here, and here is this bar again, massless bar. Okay, and again, this is distance R. Okay, this is distance R. So let's say this time here, let's say the force is applied, let's say right here. Force is applied here. Now, now R? It's not R. This looks at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like about 5. So this looks like half R, 1/2 R. Okay. So if I do the torque now, it looks like it's still 90 degrees right here, right? Still 90 degrees. So what we got here now is we have torque here is now equal to, we'll have here, it's going to be 1/2 R, 1/2 R times F, because it's being applied at, and sine of theta, the sine component, is going to be 90 degrees, or it's going to be 90 degrees, which is 1. Okay, so when we do this, when all said and done, torque is going to be 1/2 here times R times F. Okay, so we get the same torque as up here, except that we went same force, half the distance. Okay, same force, half the distance. Okay, all right, so let's do another example here. Okay. So here's our here's our fulcrum here again, and we'll go ahead and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is the distance R here, right? Okay, so this time, let's do this. Suppose 1, 2, 3, 4, 5. Suppose now we have a force here that's applied right here in the middle. So we have a force applied here, like so, and this is going to be 1/2, let's say R, like so. Okay, and let's say we have another force. Let's say it's applied right here, and let's say now it looks kind of. Let's say this is also F2. I kind of drew this kind of big, and let's say that this here is at 30 degrees, like so. 30 degrees here. All right. And it's applied at a distance R here. Okay. And just for fun, let's play a half a force here. So here we have a force being applied here. So this is going to be 1/2 force here, half the force, and also 1, 2, it's going to be 1/4 the radius. Okay. Which way is this going to rotate? So what the question is, rotate is in what direction? Okay, rotate. Which way? All right, which kind of brings us to some equilibrium situations here. So what we need to look at here, when we have multiple torques here, we have to think about this. We have to go sum of the torques, counterclock. Now, if this isn't moved, so to maintain balance, we got to say, to maintain equilibrium, sum of the torques in a counterclockwise rotation, counterclockwise, must equal the sum of the torques in the clockwise rotation. So what we do is, so we have counterclockwise equals clockwise. All right, so we're going to look at all the things going counterclockwise. So this force being applied here is going to cause a counterclockwise rotation. this here is also going to be applying a counterclockwise rotation. So we have two torques going counterclockwise, and we have one going clockwise. Which ways are going to rotate? All right, so let's go ahead and take a look at some of the torques counterclockwise. Counterclockwise. Okay, counterclockwise. Okay, let's start with this one right here. Okay, so it looks like we have 1/4 R. So we'll go 1/4 R right here, right? Times, looks like 1/2 F here. And it's going to be times the sine of, let's say, 90 degrees here. Okay, sine of 90 degrees. There we go. All right, and then we also have another clockwise for another one here, counterclockwise is going to be this one right here. Now remember, I'm going to use red. Remember now, when you have it something like this, you immediately want to draw the perpendicular component. Always do this, okay? This is the part that's actually causing the rotation. Now, even though I drew it here, it's a vector, so it's really being applied here, okay? So make sure it's here, but it's really being applied here, okay? Just keep that in mind. All right, so go back over here. So here we have, looks like a distance R. So it looks like it's a distance R here, okay? And here's F, okay? Force is like the full force here, except this time now it's going to be sine of 30 degrees. Okay, I chose 30 because it's 1/2, okay? 30 degrees. All right, so this is the counterclockwise, okay? So we can kind of simplify this real quick here and see what we got. So sum of the torques counter clockwise is right here, is going to equal, so 1/2 times 1/4 is 1/8 here. So it's going to be 1/8 RF, okay? Plus, right, we're going to do plus here, right? Plus, so this is going to be RF times the sine of 30. So it's going to be 1/2, right? RF, like so, 1/2 RF. Okay, it's going to equal common denominators. So we'll times, so this is going to be 4/8 here, right? So it'll be 4/8. If I add these together, we'll now have 5/8 RF. So this is the torque going counterclockwise. So let me use a different color pin. Let's use a green here. So now we want to do some of the torques going, let's say, clockwise now. Clockwise. Okay. So clockwise is this one right here. Okay. So this is going to be 1/2 R times F. Okay. It's a full F here. Okay. And this is going to be just simply 1/2 RF. Okay. So here we have 0.5. Okay, so now if we're not sure about this, we need to figure out what the decimal equivalent is here. We can go ahead and say that, well, 5/8, 5 divided by 8 is 0.62. So this right here is really 0.62 RF. RF. So this here is just 0.5 RF. Okay, so it looks like it's going to, so this is less, so it's going to have a net result of counterclockwise rotation. So this is going to rotate counterclockwise. And the difference will just be 0.5 minus 0.62. So 0.6, so 0.62 minus 0.5. So it's going to be, it's going to have a net rotation of 0.12 in this direction. So it's going to have a net torque of 0.12 RF in that direction. Okay, so that's kind of how you do it if you have multiple torques here. Okay, multiple torques. All right, let's hit pause real quick. All right, so we'll do, you guys try this one here. Okay, so this will be an example I want you guys to try. So let's say, here's our pivot point fulcrum here, right? And let's go ahead and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's R. R is 10 squares. Okay, so let's say we have a force. Okay, we have a force F acting here. Okay, We'll call it force F acting here. Okay. And let's suppose we have let's see, 1, 2, 3, 4, 5. Let's say we have another force acting here. Okay. And let's say 6, 7, 8. Let's say we have a force right here. We'll call this force 2F acting here. Right. This force 2F is acting here. And then let's suppose we have a force acting in this direction. Hold on, let me draw that a little bit better. Get rid of this here. Okay, let's say it's acting right here in this direction here. And let's say it's also force F, but it is at 45 degrees. 45 degrees. Okay, so tell me which ways are going to rotate and what's the torque's going to be in terms of R and F. Okay, just to help you out, remember this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this would be like, this would be R, 1/4 R here. So be 1/4 R here. This might be half R, so on and so forth. So go ahead and do this here on Edpuzzle and go ahead and tell me what the answer is. Go ahead and do a free response. All right. All right. So let's go ahead and let me kind of cross this out right here. Okay. Suppose now, let's say that okay, let's say here's this rod here again. We'll go like this here. And let's say this rod, let's go ahead and let's say that the rod is 1 meter. So R is going to be 1 meter. Okay, let's go ahead and do that. Okay, now this time, the mass of the bar, okay, we'll call it the mass of the bar is right here. Let's say the mass of the bar is, let's say, 1 kilogram. 1 kilogram. Okay, and let's say I want to apply a force right here. Okay, what force do I need to apply here so this remains in equilibrium? It does not rotate. Okay, okay, that's the problem. What's F so this remains in equilibrium? And this bar now is not massless. Okay, so way to start is we're going to assume that this has uniform density. Okay, and that's the assumption. Okay, unless they tell you otherwise. So right here is in the middle right here, right? It's going to kind of draw an X. This is the center of mass or the center of gravity. Okay, so there is a force going this direction here, and this force here is going to be the force of center of gravity. We'll call it CG for center of gravity. Okay, and this force is going to be looks like 1 kilogram here, right? 1 kilogram times 9.8, right, meters per second squared. Okay, so this is going to be the force of center of gravity. And let's go ahead and calculate what that is. Force, the center of gravity, is going to be, looks like 9.8 newtons. 9.8 newtons. Okay, so that's the force. Now, once we got the force, I need to know what is the torque. Okay, now R is going to be 0.5 meters. 0.5 meters, because that's usually what center of gravity is. It's in the middle. So the torque here, okay, we'll call it torque of center of gravity. Okay, make it center of gravity is going to be torque center of gravity is going to be so R is 0.5 right here, right? Times, okay, we'll put in parentheses here, times 9.8 times 9.8. Okay, and this is going to equal, so we'll go 0.5, 0.5. So we'll see here, 0.5 times 9.8 should give us about 4.9. Okay, this will be 4.9. Okay, let's draw this out here. 4.9 newtons. Okay, now this is going to be a what? This is going to be a clockwise rotation here from the pivot point. Clockwise rotation. So this force here has to be what to be able to match it. Okay. All right. So what we got here. So if we want to do this here, here's what we got. So we'll say sum of the torques, right, counterclockwise has to equal sum of the torques clockwise. Okay, always start with this. So counterclockwise. Okay, so this is going to be counterclockwise here, right? So here we have, that's going to be R times F here, and it looks to be 90 degrees. So we'll just go ahead and write RF, and we'll go ahead and write sine of 90 degrees just to be complete. Okay. Equals over here. It looks like over here we already calculated over here. So the clockwise torque is going to be 4.9 uh, newtons. Okay. Now I could have done this all over here too as well. Okay. Okay, I'll do another example when I actually do that. So I go over here. So R is going to be 1, okay, and times F, which I don't know what F is, and sine of theta is 1, is equal to, this is going to be 4.9 newtons. All right, so it looks like the force that needs to be applied here is going to be 4.9 newtons to maintain equilibrium. Okay, equilibrium. Equilibrium. Okay, equilibrium. All right. Okay. All right. Hit pause real quick. Okay, this next example here is kind of a teeter-totter situation here. And here, let's say we have, this is a 10 kilogram box here, and it's at the end over here, so where this is like 1, 2, 3, 4, 5. So here, looks like R is going to be, let's say, 5 meters. Let's say that each square represents 1 meter. It makes it a little bit easier. So 5 meters this way. So we have a box here. I'll go ahead and use green here. Where should I put this box here? Let's say here's a box here. There it is. And let's say that this box is, let's say, 2 kilograms. So this box here is 2 kilograms. Where should be placed some distance r from the fulcrum here so this maintains equilibrium? Okay, very good question. All right, so the way to think about this is, so over here, yeah, what's r? We don't know what r is. Okay, all right, so let's take a look at the rotation here. If I put a box here, it's going to cause this kind of rotation. Okay, and if that rotation is going to be counterclockwise, right? If I put a box here, it's going to rotate in this direction, and that's going to be clockwise. Okay, so we'll do our sum of the torques, right? Sum of the torques counterclockwise equals sum of the torques clockwise, like so, clockwise. All right, so let's go ahead and take a look. Let's do counterclockwise here. Okay, so we have a mass here, G. Okay, there's our force, mg, times some distance r over here, has to equal mg, some distance r over here. Maybe we'll call this r left. This would be r right. Okay, mass left, mass right, to the right side. Okay, so over here, this is going to be 10 kilograms, right? So we'll say 10 kilograms here, parenthesis, times 9.8. Now we can see here that the G is going to cancel out, right? But won't worry about it right now. What's R? R2 is going to be 5, R left is 5 meters. So there's 5 meters here. Equals, okay, here's the mass here, which mass we know would be is 2 kilograms. So here's 2 kilograms here, okay, times 9.8. There's 9.8 here, parenthesis, and then we'll go ahead and put in here what R is, R right. Okay, what's that going to be? All right, now when I look at this here, we can see the 9.8s cancel out. Okay, so here we have, this would be 20 over here. Okay, and this is going to be, looks like 2R to the right here, right? And so it looks like that R has to be, well, R here, R to the right has to be placed at, it looks like 10 meters away. So in this problem here, I just made this up. So if this is 5 meters, 2 kilograms is not going to do it. We have to extend this this would be 6, 7, 8, 9, 10. So the bar has to be, this would have to be extended out to, let's say 10 meters, and we will have to put the box here for 2 meters, make a connection in order for this to maintain equilibrium. So this is kind of a surprising result. I just made this up, and that's interesting. So this will not work unless I increase the mass. But if I extend this out to, let's say, 10 meters, now I can make it work to where, yeah, so I already have to be at 10 meters for this to maintain equilibrium. Okay, let's go ahead and try another example here. Okay, let's say we have this a bar here, and this bar does have mass. Okay, so here's this bar here, and let's say this bar, just to make it easy, R, let's say, is 1 meter. Okay, and let's say that we place, let's say, right about here, I I place a, let's say, 140 gram uh, block here. Okay, this 140 grams, and the bar. Okay, we'll call this the mass of the bar. We'll call it MB. Mass of this bar here is, let's say, 100 grams. 100 grams. Okay, and let's say the fulcrum is here. Here's the fulcrum right here. And let's say I'm going to place this, let's say, about right here. So here's this force here. Here's F. Okay, some force F here. And let's say that this R right here, distance, let's say, is 0.1 meters right here, right? And let's say that over here, this R, maybe we'll call this R1 here, right? Here's R1. Here's force 1. And let's say here's R1, and we'll call this here R2. And let's say from here, it's about, let's say 0.8 meters. 0.8 meters away. Now, the bar has mass. What does F1 have to be to maintain equilibrium? Okay. All right, so to do this problem here, let's go ahead and let's use red. So first of all, the bar does have mass. So this here, we'll put a little X here for the center of gravity. And we'll symbolize a force going in this direction here, because we do have a force mg that's acting in this direction, and also at some distance r. Okay, we'll call this maybe R3, just to help us out. All right, so we have to keep this in mind here. So we have mass of the, we'll call it MB. So we'll call this here the mass of the bar. So this is, I'll put a little B here for mass of the bar. Okay, so we have all this information here. So we have to kind of like do the sum of the torques. We'll say here counterclockwise must equal sum of the torques here clockwise. All right, so this is going to be counterclockwise here. This is clockwise here, and this is clockwise here as well. So we have one going counterclockwise and one going, and a couple of forces go, hold on. One force counterclockwise, two torques going clockwise. All right, so go over here. Let's take a look here. Let's do the torques here. So that's going to be F1 here. So here is F1 here, right? Times, it's like R1. It's right here. There's R1 equals, so the two torques, we'll start with this one here first. So we're going to have here mass of the bar here times G, like this right here, right? Times G times, we'll call it R3. Okay. Plus, here we have, we'll call this mass 2. So this would be mass 2. Okay. So we'll call it mass number 2 here times G times, looks like we'll call it R2. Okay, so let's plug all the numbers in and see what we got. So this is going to be F1 here, which we don't know what it is, but R1, we'll say multiply. R1 is, we'll call it, put in a parenthesis here, is a 0.1 meters, like so, equals. Now MB, is right here. And now the mass of the bar is 100 grams, so it's going to be 0.1 kilograms. So we go ahead and write kilograms here. 0.1 kilograms times 9.8. Okay, I'll be thorough here. Meters per second squared here, close parenthesis. R3 is going to be 0.5 meters because that's the center of gravity. It's a uniform density bar. Okay, plus, okay, M2 looks like is going to be 0.14 kilograms here, 14 kilograms, times 9.8 meters per second squared, like so. And we're going to times it by, looks like R2 is zero point 0.8 meters. 0.8 meters. All right, so I set this up for you. You guys go ahead and do the math and go ahead and answer it on Edpuzzle. All right, so after all said and done here, F1 needs to be about, we'll say 15.9, let's say 15.9 newtons, or you could round up to almost 16 newtons. All right, let's do one more example here, then we'll take a look at the study guide. All right, new problem here. Suppose we have this uniform density bar here that has a mass of 60 kilograms, and we have a 25 kilogram block placed at say 1, 2, 3. So about 1, 2, we'll say about, we'll call this R is equal to, okay, maybe we'll call this here mass 1. And R1, we'll say, just for simplicity's sake, is about 2.5 meters away from F1. Okay, 2.5, okay, F1. And, well, first of all, let's backtrack. So it's saying here, okay, so for this to maintain an equilibrium position, what does F1 and F2 have to be? Now, it's a rotational problem, so there's no clear identifiable fulcrum. So, like I said before, if there's no clear identifiable fulcrum, we'll make the left side here be the fulcrum. So this here is going to be the pivot. So here's the pivot right here. And let's go ahead and draw an arrow, and we'll call this here the pivot. Okay, so the pivot. Here's the pivot. I think it's IOT, pivot. Okay, the pivot. Okay, so here's the pivot. All right, so if this is the pivot here, so our R distance is going to be based on the pivot point. So we'll go about right here, which is roughly, we'll say 2.5 meters right here. Okay, now the bar does have a mass. So I need to identify the center of mass, which would be 1, 2, 3, 4, 5. So right here, this where the X is right here is going to be the center of gravity or the center of mass. We're going to say center of gravity right here. Okay. All right. So there's a force here. Okay. So what does F1 and F2 have to be so this maintains rotational equilibrium? Let me go and use green here. So now, since this F1 is the fulcrum, we're going to ignore this F1 for right now. So we're going to ignore this for now. So we have a counterclockwise rotation here. Center of gravity is going to be a clockwise, and this here is going to be counterclockwise. So we have two counterclockwise and one clockwise rotation. Okay, so before us to do this here, we have to consider, well, let's do the torques first. Okay, let's figure out what that is before we figure out what F1 and what F2 are. Okay, so, well, now's a good time to talk about Newton's first law. Okay, full Newton's first law. So we'll say here Newton's first law. Okay, generally speaking. So Newton first law. Okay, an object at rest stays at rest, or an object in motion stays in uniform constant motion as long as all the forces are in equilibrium and the torques are in equilibrium. So what this means is that we already know that some of the forces, some of the torques counterclockwise have to equal some of the torques clockwise, like so. Okay, so that's in terms of torque. Now, in terms of in terms of forces, sum of the forces going up must equal sum of the forces going down. So we have to use both of these to, this is the general expression for Newton's first law, including with rotation. All right, so let's do counterclockwise here and see what we got. All right, so we're going to ignore F1 because that's the pivot point. All right, so let's do counterclockwise. What's going counterclockwise? Looks like this one and this one are going counterclockwise. So let's go ahead and do this here. So let's go ahead and do, looks like here it's going to be 25, right? 25 kilograms here times, let's say here, 9.8 meters per second squared here, right? Times, looks like a distance of 2.5. So 2.5 meters, okay? Plus, okay? Now we have this, we did this one here, this one over here. Now it looks like, okay, so R, I forgot to mention, R is, let's say, 1 meter. I don't know if I said that or not, but R is 1 meter. So here we have F2, okay, and it's at some distance, we'll call it R, which is 1 meter. 1 meter, okay. All right, so this is some of the forces counterclockwise. Over here, we have to have some of the forces clockwise, okay. So it looks like it's just one here. It's the center of gravity here. So this is going to be, so some distance here, it's going to be 0.5 meters away. So it's going to be 0.5 meters here, 0.5 meters here. The mass is, let's say, looks like it's 60 kilograms. So here's 60 kilograms here, like so, 60 kilograms, times 9.8 meters per second squared. 9.8 meters per second squared, like so. All right. So now, let's see, let's go try to simplify this and see what we got. All right, so we do the math here. Looks like we have 612.2 plus F2 equals 294. All right, and again, so now we want to solve for F2 here. So if I do, okay, so it looks like, let's see, hold on here. Hold on, I have a typo. Whoa, big error. This can't be 2.5 meters. This has to be 0.25 meters. Okay, we have an error here because R is 1 meter. So typo here because the math didn't work out here. So this is going to be 0.25 meters. 0.25 meters. All right, go and give that a shot. All right, make that correction here. So we're going to solve for F2. So F2 is going to equal, looks like 294 minus 61.5, excuse me, 61.2, and that equals 232.8. So 232.8 newtons is what F2 is. Now, what's F1? Well, to find F1, we're going to use red. We have to use this relationship here to find F2. So we go ahead and use red. All right, so forces going up. Okay, what forces are going up? Well, we have F1 going up, plus we have F2 going up. Okay, and what are the two forces going down? Well, going down here, we have the center of gravity, which is going to be 60 kilograms here, times 9.8. Okay, and then we also have this 25 kilogram mass going down as well. It's going to be plus here, 25 times 9.8. So we're going to here put 9.8, like so. All right, so so we just found F2. So F1 here, plus this looks like 232.8 has to equal. All right, so if we do the math here, we get F1 plus 232.8 times 588 plus 245. Add these together and subtract off here 232.8, and we get that F1 has to be 600.2 newtons. So 600.2 newtons. All right. So let's go and take a look at this lecture notes here. Let's take a look at this. So this is our study guide here. And let me go ahead and make it a little bit bigger so we can see it. So again, here's torque and here's towel here being written out like this. And let's go ahead and take a look at some problems here and see what we got going on here. Okay, so let's go ahead and scroll down here. And here we have hit pause. Let me open this up with Cami real quick here, and that'll make it a little bit easier for me. All right, so here we go. Let me go ahead and let's minimize this here. Let me move this out way here. Okay. All right. So here's torque. So go ahead and read about torque here. And let's go ahead and take a look at question 733. Can we go ahead and answer this question here using this hint? All right. You go ahead and try 7.34 as well as 7.35. And then we'll talk about 7.36. Okay, 7.36. Here you have an object here, and here's the fulcrum right here. So a constant force F is being applied for 5 seconds at various locations here. Rank the magnitude of the torque exerted by the force on the object about the axis located at the center of mass from smallest to largest. Okay, and I'll kind of give you a hint. B is going to be 0 because the force is being applied at the near the center of mass. So R is going to be like 0 here. Okay, it was fairly close to that. So go ahead and think about the other ones here and kind of see what we got going on. Okay, so the answer here should have been, let's see here, should have been B here, right? Here's B, followed by C, okay? And looks like here, here's, okay, and here's D and here's A. So it looks like A, because A is at some angle. So we only want the sine component, right? So that's why it's going to be less than D, which is equidistance away from the center of mass here. So the greatest force is going to be D because it is perpendicular and it has the greatest radius or radial distance away from the center of mass. Okay. All right. Go ahead and try 7.37. Well, when they say greatest angular acceleration, remember now torque, right? Torque, which is a force times R, or here, torque is, we'll say here, R times F, okay? Whichever has the greatest torque is going to have the greatest angular acceleration. So keep that in mind and see what we got. Okay, so this is from largest to smallest. So the largest is going to be D. Okay, so there's D, and I think next is going to be C. Okay, next is going to be A, then followed by B. Okay, and kind of see if that makes sense here. Okay. Okay, 7.38 we'll do in class. We'll do this in class. In class. Actually, we'll scratch that. Here's the hint here. Why don't you guys go ahead and go ahead and try 7.3. I think it's kind of set up here for you, and you go ahead and try to do this. Okay. All right. So here's 7.39. You should be able to do 7.39. So go ahead and try that one. And we'll go ahead and pause here.